Problem Introduction. Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 27, Remove Element. This is a medium-level problem, often categorized under dynamic programming, although we'll see a clever approach that avoids nested loops. The problem statement asks us to remove all occurrences of a specific value from an array and return the new length of the array. Sounds simple enough, right? But the catch is, we can't use extra space proportional to the input array. We need to do this in place, meaning we modify the original array directly. Think of it like cleaning up your room. You're rearranging existing things, not bringing in new boxes to sort. We'll explore different approaches, understanding the constraints, and aiming for the most efficient solution. Let's dive in. Understanding with examples. Let's solidify our understanding with some examples. Suppose we have an array nums equal to 3, 2, 2, 3, and we want to remove the value 3. After removing all instances of 3, we should be left with 2, 2, and the function should return 2, representing the new length. Another example, if nums is 0, 1, 2, 2, 3, 0, 4, 2, and we want to remove 2, the result would be 0, 1, 3, 0, 4, with a returned length of 5. See how we're only changing the array in place, not creating a completely new one. We only care about the elements that remain, and the resulting length tells us how many of those we have. Now that we've seen how it works, let's move on to the different ways of solving this problem. Brute force approach. A straightforward approach would be to iterate through the array and create a new array, only adding elements that are not equal to the target value. This works, but it's not optimal because we're using extra space. We need to adhere to the in-place modification constraint. Imagine trying to sort a deck of cards by setting aside all the cards of a certain suit and creating a new deck. It's not very efficient. Another brute force method might involve iterating through the array and swapping elements that match the target with elements that don't. But this method can still lead to unnecessary complexity in terms of time and multiple passes. Let's focus on a more efficient solution to bypass these issues. Optimal solution. The optimal approach uses two pointers, a slow pointer and a fast pointer. The fast pointer iterates through the entire array. If the value at the fast pointer is not equal to the target value, we copy it to the position indicated by the slow pointer and increment the slow pointer. This cleverly modifies the array in place. Think of it like tidying your desk. The fast pointer is you looking at each item, while the slow pointer keeps track of where the organized items go. If the fast pointer finds something that doesn't need to be removed, we move it to the organized location indicated by the slow pointer and proceed. It's a very efficient way of removing elements without using additional space. Code implementation. Let's see the code in Python. We'll define a function, removeElement, that takes the nums array and the target value val as input. We initialize the slow pointer k to 0. Then we iterate using the fast pointer I. If nums at position I is not equal to val, we assign nums at position k to nums at position I, and we increment k. Finally, we return k, which represents the new length of the array after removing all occurrences of val. It's concise and efficient. Remember to consider edge cases, like an empty array or when the target value is not present. Time and space complexity. Analyzing the time complexity, we see that our solution makes only one pass through the array. This makes our time complexity O of n, where n is the length of the array, highly efficient. Regarding space complexity, we're modifying the array in place, so we only use a constant amount of extra space for our pointers. That means our space complexity is O of 1. Compared to the brute force approaches that might have O of n squared time complexity, or even O of n space complexity, our solution is a significant improvement. Engagement break. So, what did you think of this approach? Did you find the two-pointer method intuitive? Let me know in the comments below. And if you found this video helpful, don't forget to hit that like button and subscribe for more LeetCode solutions and coding tutorials. Share this video with your fellow coding enthusiasts to help them level up their skills too. Let's keep the coding conversation going. I'd love to hear your feedback and ideas for future videos. Conclusion. We've successfully solved the remove element problem on LeetCode, focusing on an optimal approach that meets the in-place modification requirement. We learned about the